tells us how far out from the circle we need to go. And then theta tells us at what angle we need to place that specific point. And it doesn't matter which order you plot them, as long as you stay consistent. So our first point is 3 and then 5 pi over 6. So starting at the center, I'll go 3 rings out, and then I'll find 5 pi over 6. And of course, 5 pi over 6 is in the second quadrant at 150 degrees. So start at the middle, go 1, 2, 3 at 5 pi over 6. So now I have A. Point B is -2 pi over 4. So this one's kind of interesting because I have a negative value. So what that means is that instead of going to within the ring, we're going to go backwards, reflecting across the origin that many rings. So I'll start at pi over 4, which of course is here. And instead of going 2 rings here at pi over 4, we're going to go backwards, reflecting across. 1, 2. So this really over here is B. Part C is 3 pi over 6. So I find pi over 6 and then go 3 rings, 1, 2, 3 out. D, very similar. I'm at pi over 3, which we know is here. Pi over 3 is here. However, instead of going +2, we'll reflect over the origin and go 2 out, the opposite. And then E, of course, we've got 3 pi over 4, which is 135 degrees. And then we're going to go 4 rings out. 1, 2, 3, 4. However, we also could say that this value could be the same as -4, 7 pi over 4. So if I were to plot 7 pi over 4, which is here, and instead of going 4 units, instead of going 4 units, for some reason it's moving on me. Okay. Instead of going 4 units towards 7 pi over 4, we go backwards, which lands us to the 3 pi over 4, which also similarly, I could also write this -2 pi over 3 for part D here. I could write this as the same as +2 and 4 pi over 3. So I would go to 4 pi over 3 and go 2 rings down. So each polar coordinate could have two different points to it, if you will. And those are equivalent points depending upon which direction you're moving. All right, a little bit of a review, because polar coordinates, although they can be useful, similar to the difference between using radians and degrees, most of us are more familiar with the Cartesian plane over the polar coordinates. And so is there a way that I can convert back and forth between being polar and then Cartesian? Because I think we can visualize the Cartesian plane much more easily. So cosine, sine, and tangent is what I grabbed from what we define as cosine, sine, and tangent with respect to our 90-degree triangles. But I also know that if I wanted to solve each one of these for its specific variable, our top one, x, would be equal to r times cosine of theta. Y would be equal to r times sine of theta. And I could rewrite, well, tangent that has x and y because of its location, but these are also related as x squared plus y squared is r squared, because we have the right triangle using Pythagorean's theorem. Find the Cartesian coordinates of a point with the polar coordinates 5, 2 pi over 3. We know that 5 is our radius, and I know that 2 pi over 3 is our theta value. And if I'm looking for the Cartesian plane, I'm looking for x y. Well, in order to find x, I can use this particular formula here, where I know that x has to be our radius times cosine of theta, both of which I know. So I know x is equal to 5 times cosine of 2 pi over 3. And similarly, I know y is equal to the radius times sine of our theta. All right, well, I know what sine and cosine of 2 pi over 3 is. I can grab my unit circle that we created quite a few weeks ago, unless you've got those memorized, of course. And I know that 2 pi over 3 is the same as negative half. So this gives me 5 times negative half, or negative 5 halves for my x value. And then my y value at sine of 2 pi over 3 is square root 3 over 2. So of course this would be 5 square roots 3 over 2. So my x and my y value, of course, are negative 5 halves, 5 square root 3 over 2. And now most of you'd be able to like visualize where in the Cartesian plane would this look, right? As opposed to 2 pi over 3, which also is pretty easy. I mean, now that we've plotted them, it takes some time getting used to, but certainly doable. Let's try another one. So this one, it says find the Cartesian when we have 2 as our radius and pi as our theta value. All right. X is equal to our radius of 2 times cosine of pi, our theta. Well, I know that cosine of pi is negative 1 by looking at my unit circle, or maybe again you've had some of those pieces memorized at this point. We've used them so often. Is negative 2. And y is equal to the radius times sine of pi, which of course would be 2 times 0, or 0. So our coordinates in the Cartesian plane are negative 2, 0, right on that x-axis on the left-hand side. We can, of course, go the opposite direction. So I just brought these over. They're already in specifically our notes. But what if I'm given the x and the y, and I want to find the polar coordinate that matches, right? I want to find the polar coordinates that match. So I know that negative 3, negative 4, this is in the third quadrant. So I'm just going to make note of that because we'll come back to that third quadrant. Well, utilizing any one of our equations such that x is r times cosine of theta and y is r times sine of theta, and of course just bringing these over, x squared plus y squared equals r squared. Well, if I'm going to put anything back into polar coordinates, I definitely need both r and I need theta in order to put things in polar coordinates, both of which I don't have. But I do know that I can find my r value by using Pythagorean's theorem with respect to our r, finding r. All right, so in this case, we'll have negative 3 squared plus negative 4 squared equal to r squared, what we're trying to find. 9 plus 16 is r squared. So therefore, r has to be 5. So we have part of the battle in order to find the polar coordinates. Let's just put it here, 5 what? So I need theta now. Okay. It doesn't matter which value that we specifically utilize, but I do know that cosine is our x value over our radius. So I could use this formula, or I could use y over r. Doesn't matter, I'll just use cosine. But if you're gonna use the second one, you'd have to obviously use sine to do that. So I know that cosine of theta is equal to my x value over what we just found our r value of 5. Okay. Well, -3/5 is not on our unit circle, so I need to evaluate that. So so if I want to find theta, I want to find the inverse of cosine of -3/5 on our calculator in radian mode. And I'll get theta is equal to 2.214. Right, but if I'm thinking about what this looks like, 2.214 is in the second quadrant, right? Because here's pi, so there's 3.14, so we're just shy of pi. I need to be again in the third quadrant, which is fine because I also know that cosine can be negative in the third quadrant as well. So I want to find what is this particular theta value for the one in which we're looking for. And I can find that particular value by taking 2 pi minus 2.214, and we'll get about 4.069, which is in fact the theta value that we need to be in the third quadrant. And thus our polar coordinates are 5, 4.069. So not always nice and neat within our graph around the specific circle. Let's try, oops, there was 2 of them there. I apologize. I need to go back here. And of course I put my picture in the wrong area too. All right, let's just change the colors. All right, so find the polar coordinates with the Cartesian coordinates of 0, -4. So again, we have x, y. We need to find a radius and we need to find theta in order to find our polar coordinates. So I'll first start off by finding r, since I know that x squared plus y squared is r squared. So 0 squared plus -4 squared is r squared. 16 is r squared, so our radius has to be 4. Okay. Now, when I'm looking at the two values, 0 and -4, I definitely could find where sine or cosine is 0 in order to help easily solve this more efficiently. So I'm going to choose my x value, which means I'm going to utilize cosine, because I know x is 0 and I know my radius is 4, and this will help me just be more efficient finding a nice neat number. So I'll say, well, I know that cosine of theta is our x value over the radius of 4. So theta has to be equal to the inverse of cosine. Well, 0 divided by 4 is just 0. So where on our unit circle is in fact cosine equal to 0? We know that there's 2 locations, right? So theta would have to be 3 pi over 2 or pi over 2 are the 2 locations. Notice it doesn't tell us within the directions a specific quadrant, right? Because 0, -4 is in fact on the y-axis down below. So we want to look for the one where it is down below. And that one in fact would be 3 pi over 2, but also knowing that we can reflect. So this could also be -4 pi over 2, right? Thinking about 0, -4 is down below, and where we need to go just reversing opposites and going across the origin. Part 6 is asking us to sketch the graph of the polar equation r is equal to theta. And we're going to grab Desmos to do that. And I'm going to come back to here so we can fill in some notes a little bit. Let me share this tab instead. And I'm going to say r is equal to theta. So I need to find theta in my ABC button. Here it is, right above the backspace. right now my graph is in the Cartesian coordinate system. If I go ahead and click the graph settings, a little wrench, I can change it into polar coordinates. And what I like about this is it certainly gives you around the outside our unit circle pieces, and we can see the decomposition of the circles themselves. There's also a lot of cool features here as well. What I want to showcase though is when theta is 0, so we're right in the middle, of course our radius is 0. And we can zoom in a little bit here so we can see a little closer to the numbers. When our radius is, when theta is pi over 4, and of course we know pi over 4 is at 45 degrees, so here, even though it's not listed, it's interesting because our radius will also be the same, right? Because our radius is equal to theta. So whatever our radius is, theta has to be. So as I switch back to our notes, just to kind of make a little statement about that here, making a theta radius table, if you will, instead of XY, theta radius. When theta was 0, our radius was 0 because they're equal to each other. So when our theta was pi over 4, our radius would also have to be pi over 4 because they're equivalent to one another. And of course, if it's helpful, we have 0.785, like the decimal version of the radius. And this will continue all the way around all the way around. Now, when I look at example 7, our radius is always 3. So it doesn't matter what theta is because our radius will always be 3 no matter what that theta value is. So I'm going to graph or just kind of think through here what might look like. So when theta is, let's say, pi over 3, our radius will always be 3. If we are at pi over 2, our radius is always 3. If we are at pi, our radius is always 3. So it doesn't matter where I am around my circle, our radius will always be 3, which makes sense because the circle, if we think about a circle, it's circular in nature. So if I might graph this, 1, 2, 3, it doesn't matter what our theta is, our radius will always be 3. So it's going to be a circle. Popping us back over to Desmos to verify. Oop, we got to zoom out a little bit. I see that circle. So it doesn't matter again what our radius is, our theta is, our radius is always going to be 3. It's going to be cyclical, just kind of going around and around and around in a circle forever.